Rising demand on food requires farmers on global-wide need to shift from traditional labor-intensive farming to data-driven and technology-based agricultural practices. Smart agriculture technology such as auto-irrigation system, sensor monitoring and precision farming can help farmers optimize their farm management practices, thus increasing crop productivity and reduce labor dependency. By integrating this technology, we directly align with the United Nations Sustainable Development Goals (SDGs). Our efforts actively drive SDG 2 Zero Hunger by increasing food production and food security, SDG 4 Quality Education through the development of knowledge and technical skills, and SDG 15 Life on Land by focusing on sustainable resources management and reducing environmental impact. Ultimately, smart agriculture kits can help farmers understand on how to optimize farm management through real-time monitoring and automation, enhancing decision-making and operational efficiency.
To address the diverse challenges of modern farming, this practical is structured around 5 core technical objectives. Our goal is to demonstrate how smart technology can enhance agricultural efficiency and productivity through data-driven solutions. First, our objective is to develop an automated irrigation system by integrating a soil moisture sensor and a water level sensor. Second, our objective is the precise measurement of environmental variable by utilizing the DHT11 sensor. Third, focus on maximizing crop yield by automating artificial lights. In case 4, our objective is to establish a robust farmland protection device by combining a PIR motion sensor and ultrasonic sensor, followed by triggering of a light and buzzer alarm. Fifth, for case 5, our objective is to monitor aquatic health by using a waterproof DS18B20 sensor to measure water temperature and provide constant update on an OLED display screen to ensure stable condition for aquaculture.
For procedure for Case 1 auto-irrigation in farmland, the first step is to attach the microbit to IoT bit. Then, the GVS 3-pin DuPont wires were attached to both sensors. Next, the servo was connected to pin P9 on IoT bit. And then, the soil moisture sensor was connected to pin 1, while the water level sensor was connected to pin 2. Pins P1 and P2 were selected for the soil moisture and water level sensors because they are analog-capable pins on the IoT bit. This is essential for converting the variable voltage from the sensors into digital data that the microbit can process. Next, the USB cable was connected to the IoT bit and then connected to the laptop. And then, the code was downloaded as shown. The water level status was successfully displayed on the microbit. Whenever the soil became dry, the servo was automatically triggered to start watering. For procedure for Case 2 temperature and humidity monitoring in greenhouse, the first step is to attach the microbit to the IoT bit. And then the GVS 3-pin DuPont wire was attached to the DHT11 sensor. Next, the servo was connected to pin P1 on IoT bit. Then, the USB cable was connected to the IoT bit and then to the laptop. Lastly, the code was downloaded. The OLED screen was observed to update and show the current temperature and humidity values correctly. For procedure for Case 3 artificial light for agriculture, the first step is to attach the microbit to the IoT bit. And then, the GVS 3-pin DuPont wire was attached to rainbow LED. Next, the rainbow LED was connected to pin P1. The USB cable was connected to IoT bit and then to the laptop. Lastly, the code was downloaded as shown. When the ambient light became low, the LED was automatically turned on. When sufficient light was detected, the LED was turned off. For procedure for Case 4 farmlands protection device, the first step was to attach the microbit to the IoT bit. And then, the GVS 3-pin DuPont wires were attached to 3 of the sensors. Next, the rainbow LED was connected to pin P9 on the IoT bit. Then, the PIR sensor was connected to pin P2 on the IoT bit. Next, the sonar bit was connected to pin P1 on the IoT bit. After that, the USB cable was connected to the IoT bit and then to the laptop. Lastly, the code was downloaded as shown. When a person approached within the defined distance threshold, the red LED was illuminated and the buzzer sounded. For procedure for Case 5 water temperature detection, the first step was to attach the microbit to the IoT bit. Then, the OLED display was connected to the IIC port on the IoT bit. Next, the DS18B20 waterproof temperature sensor was connected to rainbow LED, then to GVS3 pin DuPont wires. After that, the wire was then connected to pin P1 on IoT bit. Then, the USB cable was connected to IoT bit and then to the laptop. Lastly, the code was downloaded as shown.
Inside a forever loop, the system reads P1 as soil moisture and P2 as water level, and then continuously displaying the water level on the LED matrix as a bar graph scale 100. If soil moisture drops below 30, then the P9 servo rotates to 180 degrees to open the watering valve and pausing for 500 milliseconds. Otherwise, the servo returns to 0 degrees to close the valve with an identical pause. This cycle repeats endlessly to automate irrigations while maintaining visual water level monitoring. This microbit program functions as an automated environmental monitor by utilizing an external DHT11 sensors to track climate data and displaying the result on an attached OLED screen. Upon booting up, the on-start block initializes a 128x64 pixel OLED display and lights up a grid pattern icon on the microbit built-in LED matrix to signal that the system is ready. The program then enters a continuous forever loop that first reads the ambient temperature in Celsius from the DHT11 sensors wired to pin P1 and then save it to a variable named temperature, then wait for 5 seconds. Next, it reads the relative humidity percentage from the exact same pin, then save it to the RH variable and waits for another 5 seconds. Finally, the loops clear any old text from the OLED display and use string concatenations to print the updated readings side by side with their respective temperature and RH label, and then constantly refreshing this sensor data roughly every 10 seconds. This microbit program creates an automated light-sensitive indicator by controlling a single programmable NeoPixel LED based on the surrounding environment brightness. During the setup phase in the on-start block, the program initializes an addressable NeoPixel strip with exactly one LED connected to pin P1 using the standard RGB, which is the GRB format, color configuration, then saving the setup into a variable name strip. Once configured, the program transitions into a continuous forever loop that monitors ambient brightness via the microbit's built-in light sensor. It evaluates an if-else condition, which means if the detected light level drops below a threshold of 100, which indicating a dark environment, then the program triggers the trip to show the color red as a warning or night light. Otherwise, if the ambient light is equal to or greater than 100, it will switch the LED color to black, which effectively turns the NeoPixel off. This microbit program controls a smart security or proximity alarm system by combining data from an ultrasonic distance sensor and infrared sensor to trigger an LED ring and a buzzer. In the on-start block, it initializes a 24 LED NeoPixel ring connected to a pin P9 using the standard RGB format configurations and assign it to a variable called strip. Inside the continuous forever loop, the microbit constantly tracks its environment by saving the distance reading from an ultrasonic sensor on pin P1 into ultrasonic distance, which is measured in millimeters, and reading the digital state of an IR sensor on pin P2 into a variable called IR. The logic utilizes nested condition statement, which is first it checks if an object is within a specific close range zone between 10 mm and 100 mm. If an object is detected within this distance threshold, it checks a second condition to see if the IR sensor reads a digital high value of 1. If both sensor conditions are met, the NeoPixel ring lights up red, which is a wedding musical melody will place in the background. And the program pauses for 1 second. If the object moves outside the distance boundary, or if the distance is correct but the IR sensor does not detect anything, then the program defaults to turning the NeoPixel ring black, effectively keeping the alarm deactivated. This microbit program set up a continuous digital thermometer that reads temperature data from a specialized sensor and displays it in real time on an external screen. Upon initializations in the on-start block, it configures an attached OLED display with a resolution width of 128 pixels and height of 64 pixels. The program then transitions into a repetitive forever loop where it communicates with a DS18B20 water-resistant temperature sensor wired to pin P1, reading the current ambient temperature in Celsius and saving that value into a variable named temperature. Immediately after acquiring the reading, code clears any older text off the OLED screen to prevent visual overlapping and then utilize a string concatenations join block to output the label temperature, followed by the actual numeric value stored in temperature. Notably, it used a show block to print this data on a single continuous line, after which the loop paused for 5000 milliseconds before restarting the sequence to fetch and display an updated temperature reading. In case 1 auto irrigations in farmland, the soil moisture sensor provided continuous real-time data that enables threshold-based irrigation. A threshold of 30 was selected because many common crops such as maize, tomatoes, and leafy greens experience tomato closure and reduce photosynthesis when soil moisture falls below approximately 30% of field capacity. By triggering the servo to open the valve only when moisture dropped below this level, the system prevented both drought stress, which can reduce yield by 30 to 50%, and over-irrigation with waste water and cause nutrient leaching. The water level bar graph displayed on the microbit allowed the farmer to visually monitor tank status and preventing dry run damage to the water pump and ensuring uninterrupted irrigation. Compared to traditional type irrigation, this closed-loop system improves water use efficiency by an estimate 30 to 40% directly contribute to sustainable water management and consistent crop yield. A possible error that can occur if the soil moisture sensor was inserted too shallow. It will measure the surface moisture rather than root zone moisture that can lead to premature watering. This can be avoided by inserting the sensor by approximately 5 to 10 cm in the soil. On the other hand, water level sensor is not fully submerged or placed at wrong height that cause fault bar graph reading on the microbead. This could lead to the farm running dry if the sensor was too low or unnecessary alert if placed too high, both reducing irrigation reliability and water efficiency. In case 2, the DHT11 sensor provides real-time temperature and humidity data displayed on the OLED screen. Different crops have specific optimal growing range. For example, tomatoes thrive at 20 to 25 Celsius and 60 to 70 relative humidity. By continuously monitoring these parameters, the farmer can intervene early when conditions deviate. For instance, by opening vents, turning on fans, or activating misters. This could prevent heat stress and fungal disease caused by excessive humidity such as powdery mildew. Although this case did not include automatic actuators, the visual display alone improves resource efficiency by enabling precise, on-demand climate control rather than scheduled or gas-based adjustment. Consequently, energy used for heating, cooling, and humidification is minimized while crop quality and yield are maximized. Placing DHT11 too close to the microbead, which generate heat, can artificially increase the temperature about 2 to 3 Celsius, which could cause farmers to unnecessarily cool the greenhouse and waste energy. This can be corrected by positioning the sensor 10 to 20 cm away from the heat source. Other possible error was the lack of OLED initializations in the code, which caused the display to remain completely blank even though the DHT11 sensor was correctly reading temperature and humidity. The microbead built-in light sensor measured ambient intensity and controlled a rainbow LED. A threshold of 100 was chosen because photosynthetic active radiation below approximately 100 micromole per second limits carbon fixations in many vegetables. By turning on the LED only when natural light was insufficient, the system extended the daily light period without wasting electricity during daylight hours. This is particularly valuable for leafy greens such as lettuce, spinach, and indoor or greenhouse production during winter months. The result is about 20 to 30% reductions in lighting energy consumption compared to fixed timer system, while maintaining or increasing biomass accumulation through supplemental lighting. Thus, the system improved both energy efficiency and crop yield per unit area. Error that can occur during coding, the threshold level was set too high, which can cause the LED remains open even during daylight, thus wasting electricity. Choosing a relevant threshold based on photosynthetic active radiation can solve this issue. In case 4, the PIR sensor and ultrasonic distance sensor work together to detect approaching humans. When motion was detected within a defined distance threshold and the PIR sensor confirmed infrared activity, the rainbow LED turned red and the buzzer sounded. While this device does not directly improve crop yield or water or energy efficiency, it protects agricultural assets from theft, vandalism, or unauthorized entry. In real-world farming, crop loss due to intruders can reach 10 to 30% in unprotected field. By providing an immediate visual or audible deterrent, the device reduces labor costs for manual guarding and prevents yield loss. Error possibility that can occur is when the ultrasonic distance threshold is set too large. it can trigger alarm for people far away that has no immediate threat, leading to nuisance alarm. By setting a reasonable threshold and combining sensor and our own logic can reduce false alarm. In case 5, the DS18B20 waterproof sensor measured water temperature and displayed it on the OLED screen every 5 seconds. For aquaculture, fish are poikilothermic, their metabolic rate, feed conversion efficiency, and immune function depend directly on the water temperature. For example, Nile tilapia grows optimally at 27 to 30 degrees. Temperature below 20 degrees Celsius reduce feeding and increase mortality risk. By providing continuous real-time temperature data, the farmer can take corrective action by adding warm water, adjusting heaters, or shading ponds before stress occurs. This can prevent mass mortality and improves feed conversion ratio (FCR), directly enhancing yield per pond. The 5-second refresh rate is sufficiently fast to detect rapid temperature changes, especially during cold night or heat wave, by allowing proactive rather than reactive management. A possible error was that the DS18B20 sensors was not fully submerged or was touching the bottom of the container, which causing it to measure air temperature or container surface temperature instead of the true water temperature. This was overcome by fully submerging the sensor in mid-water and securing it away from the container walls and bottom. In conclusion, this practical successfully demonstrates the application of smart agriculture technologies using the Microbit Smart Agriculture Kit across 5 different cases. Each case achieved its intended functions by integrating sensors like soil moisture, DHT11, light sensor, PRL, ultrasonic, and DS18B20, and integrating actuators such as servo, LED, buzzers with appropriate programming logic. Overall, this practical exercise confirmed that low-cost sensor-based automation can significantly enhance crop yield, reduce resource waste, and improve farm management, laying a strong foundation for further innovations in precision agriculture.